So here is the coup de grace of what we're studying today. We're studying a thing called a Markov chain. Okay? A Markov chain is a matrix where the rows of the matrix represent different outcomes as probabilities for a scenario. Now, because we studied probability distributions, here's what you need to know. The one thing that you really need to understand is that the rows must total to a probability of 1. Now, for you guys, I want you to imagine that we have these rows. So here is what we're going to do. Here is an example of a Markov chain. A Markov chain is just a matrix that has all of these things happening. So the last thing that I should let you know is that every Markov transition is Markovs are always square. And that's because we're always going to multiply them against other matrices or any possible scenarios that we always have. Okay? So, for example, this is my first Markov chain. So let's say I have P is equal to 0.5, 0.5, and 0.4, and 0.6, right? You want to check to see if this is a Markov chain. So you add up all the first rows, and yes, it works. Add up all the second row, and it works. It totals to 1. Okay, now here is the problem. Now, these Markov chains help us figure out what probabilities are for a certain concept, right? So imagine I give you that. That is your Markov chain. So now we're going to make a problem up based on this Markov chain. All right? So, all right. So imagine that you have the transition matrix P that we talked about before, which looks like this, which is what we talked about before. And we have the initial probability vector representing something that you know a probability for, okay? Now, you'll notice that the probability vector is always a single row of vectors that always total up to 1, like this, okay? So I got 0.6, 0.4, and 0.6. Now, when we find the first and second step probability, this is very similar to what we called a stochastic process. So remember when we did our stochastic process, we always took one thing, multiplied it, did a whole bunch of stuff, and then got our answer, right? This is the same thing, except what's happening is this transition matrix that we have here, when we have our first transition, we're actually taking our first transition and multiplying it by this. So it would be 0.46 times this. Now, when we want to go and find the second transition adjusts the probability by figuring out what P squared is. And I'll show you what I mean by that right now. So when we want to find the first probability, let's call it the first step probability. is always our initial. So I'll call that my starting value, which is 0.4 and 0.6 matrix. And then we have our P matrix, which was this. So now when we look at this, right, you've got the first step probability is literally S times P using matrix multiplication. So we've got 0.4 times 0.6 times 0.5, 0.5, 0.4 times 0.6. You multiply that out and you end up with the following answer: 0.44 and 0.56. Now, each of those columns in a problem that I would give you would represent the initial probabilities of coming up with something, but the transition matrix tells us what would happen over time. So after the first transition, this is what our probability is. Our probability for the first instance is 44, and then the second part would be 0.56 or 56%. So now let's go and take a look at the second step probability. And then the third, and then the fourth, and then the fifth. And you'll see what I mean by that. So when we're looking at the second step probability, what I'm actually talking about is what happens for P squared. So we literally have to just calculate P times P. So P squared is the same as P times P, which is just our matrix column. Now, you do your calculation, right? And when you do your calculation, you're going to get the following for P squared. You're going to get 0.445, 0.555, 0.444, and 0.556. Okay, so now we still take our initial probability vector, right? And all we're going to do is, for the second step probability, we're going to take what we have for our initial vector and multiply it by P squared. So if I was looking for the third step probability, I would have had to have multiplied my Markov transition matrix, the P value, 3 times, right? So now our initial vector is 0.4. So imagine there's a company that says, hey, I'm successful at selling my cars 40% of the time, right? And then what would happen after the second time of you trying to sell a car? So what we're going to do is we're going to take our P squared and our S, and what we're going to do is we're going to multiply them together. So it's kind of like S times P, which is going to equal this: 0.4 times 0.6 times the quantity of P squared, which is 0.445 times 0.5555 times 0.444 times 0.556. When you do your computations for multiplying these two matrices, you'll notice that these two matrices are going to work for multiplication because this one has the same number of columns and this one has the same number of rows. So we're going to get another matrix, but our final matrix is going to be a one row by 2. Okay, so here's what we get. So when multiplying those, you're going to get the following answer: 0.444 and 0.556. So what it's saying is, if I was looking at that guy that was trying to sell his car, after the second moment, second step probability of using this Markov probability of successfully selling cars, we end up with 0.444 as our probability of possibly selling cars. And he's still sucking at selling cars because he's losing. He's always failing at 55.6%. All right, and that's it. So what you're going to do in today's lesson is you're going to identify things that are Markov chains, and then you're going to do one question that deals with a rental car company.